My name is Tiffany Montague. For those of you who don't know me, I manage some of Google's space initiatives, which include, of course, our relationship with NASA and Google Lunar Xprize. It is a great pleasure that I can welcome my dear friend and mentor, Pete Worden, Dr. Pete Worden, here today as our guest speaker. Pete's had a great career in both the Air Force, where we met, former Brigadier General, and now at NASA. He is a recognized authority on space issues and planetary defense, and many would say a space visionary. On a personal note, Pete has been a great friend. He has been a fantastic mentor through my Air Force career. He pinned on my captain's bars. He eats bugs with me solely for bragging rights. And I fondly remember Pete as being the only person to have screamed his lungs at me through a satellite phone as I sat in a yurt in Mongolia, somewhere in the Gobi Desert. Without further ado, my dear friend, Pete Worden.
Thanks, Tiffany. By the way, I have to point out that Tiffany won the bug eating contest with the snake blood and whiskey drinking. The previous winner was me with the fried bat in Philippines, so we're working on some other things. That's why we're hoping to find alien life on Mars. But anyhow, I'm really delighted to be here at Google to talk to you about a very important topic, and I'd also like to say hello to everybody in the cyberspace, in the YouTube world. But what I'd like to talk about is an area that I think gets far too little attention. It's the role that NASA plays and has played and will play in the environmental issues and problems and solutions that face us. And this is, of course, a very topical issue. And it kind of got started a few years ago. A long time ago, I would say before I was born, but I was about 18 when this happened. The United States used to go deep into space. This was Apollo 8. In December of 1968, it was on the pad a few days from this date. It launched, and it went to the moon. This was probably, next to Apollo 11, the most significant human mission that we ever took. As hundreds of millions of people followed this around the world, and as the astronauts showed up in lunar orbit. But the reason I put this up here is that not so much what they did on the moon or what they saw on the moon, but what they saw from the moon. This picture, I think, may be the most important picture ever taken, at least from space, and maybe ever taken, period. Because for the first time, humans saw the Earth rising over an alien planet that really started us thinking about, we're all on this little blue spaceship, and it looks awfully small and awfully fragile. And it was, I think, the beginning of a lot of the movement and understanding of what's going on the Earth and focus on the Earth. And this is a effort that is really beginning to pay major dividends. But again, I'm not sure how much the public or even the professional community understands the degree to which NASA has started this understanding of the real role that we're going to play. So let's move ahead to today and kind of ask the question is, what has NASA done to build on this legacy that we began 40-some years ago? Well, I think we've done a lot. We spent over $25 billion on Earth science in the last 20 years, and we manage a constellation of spacecraft that consists of 14 operational satellites, 7 missions in development, and over 1,700 research grants. In fact, NASA's Earth science program exceeds the combined efforts of all other Earth sciences programs in the world. We observe Earth systems from the land. and ecosystem processes to the oceans and atmosphere. And all of these are the systems that determine the Earth's climate. And this is one of, I think, what our head of science a few years ago called one of the government's best kept secrets. And so when people say, what is the U.S. government doing on this, the fact is quite a little bit. And in fact, we're going to do a lot more, and I'll talk a little bit about what we're doing and what more we're going to do. Now, probably the most significant set of spacecraft is what in typical imaginative NASA speak is called the A train, to be followed by the B train. But it consists of a series of satellites that are in the same orbit that follow each other by a few minutes. And in some cases, 12 hours out of phase, so we can observe day-night cycles. The first satellite is Aqua. It's a great big satellite. It's got multiple instruments, but it measures precipitation rates, humidity profiles, temperature profiles, sea surface winds and surface temperatures, ice temperatures, snow, soil moisture, and so forth. On it, it has an instrument called MODIS, which may be our most important Earth imaging system that images the entire Earth in 36 spectral bands with about 250 meters per pixel resolution. There's a twin MODIS on another satellite called Terra, which I'll show you in a second. And I want to emphasize that some of these satellites are built by our colleagues and partners around the world. Aura is an upper atmosphere satellite that measures the troposphere, the stratosphere, and mesosphere. It measures temperature, dust, ozone, and essentially all the reactive chemical species. So this is the one where we study items like the well-known ozone hole over the Arctic and Antarctic regions. Another satellite is the French CNES satellite Parasol, which is a kind of a first of a new series of technology satellites called a microsatellite. This is an area that we're really focusing on at NASA, and particularly at NASA Ames. These are things that rather than weighing thousands of kilograms, they weigh tens to hundreds of kilograms and can do a lot of really interesting work. This microsatellite studies the details of cloud aerosol, including droplet size, shape, density, and turbidity. So this is a way to measure what's the effect of pollutants in the atmosphere on cloud formation and water processes. CloudSat is a cloud profiling millimeter wave radar that's 1,000 times more sensitive than typical centimeter wave radar, and it can distinguish between cloud particles and precipitation. The Orbiting Carbon Observatory is the next one that's going to go up. It's a mission being developed by our colleagues to the south, the Jet Propulsion Laboratory, and it's the first ever space-based measurement of atmospheric carbon dioxide. And this really should put to rest any residual discussion about what's going on in the atmosphere in terms of carbon dioxide, because it makes coincident, co-registered, and nearly simultaneous science measurements from a whole range of instruments. Now, each of these satellites are aligned in orbital positions, so the instrument fields of view overlap. From one satellite can be correlated to the others, and with data from each other. So the whole sum of these is greater than the sum of its parts. Now, I'm particularly personally gratified by this capability because about 15 years ago, I had a job in Washington at some place called the White House. You might have heard of it. I think there's a new occupant moving in a month or two. But I was on something called the National Space Council, and we were there to coordinate all of the civilian and military space programs. And at that time, NASA wanted to build a giant 50,000 pound satellite. It was going to hang all these instruments on it, sort of a Christmas tree decorated with dozens, if not hundreds, of instruments. And I and a few other colleagues fought very hard to break this thing up. Now the Earth science community thought we were all evil, that we just wanted to steal the money to go spend it on space exploration, which we did. But the key thing was that by forcing these guys to go to small satellites and smaller satellites, we've now made this a much more flexible system that can be easily upgraded as we develop new instruments, new technology, and bring in new international partners. Again, as I mentioned, there's not much in the way of foreign satellite data yet, and whenever I go to an international meeting and get beaten up, how come the U.S. government's not doing more on Earth science, my first point is, okay, when you folks start to match us, then we'll talk about what more we can do. Although I do want to emphasize we are going to do a lot more here in the next few years. Let me kind of turn to a very interesting immediate topic, and this is one that probably was ignored until a few years ago, and that's the ice balance in the Arctic and Antarctic. Till a few years ago, this was sort of a minor issue. We didn't think that we really could measure very much, and it wasn't very important. But for the last 4 or 5 years, this satellite called IceSat, another imaginative NASA name, measures the ice levels and altitude of ice to typically a few centimeters to a few tens of centimeters. So it can measure the ice balance throughout the world with a laser altimeter and get these very, very high accuracies. Now, this is what we've begun to discover, and this is actually quite concerning. You've probably read about some of this, but we're continuing to do this. And this depicts the changes in elevation of the Greenland ice sheet derived from the IceSat-1 between 2003 and 2006. The pink and red regions indicate a slight thickening, while the blue and purple shades indicate thinning of the ice sheets. And the current estimates say that the complete loss of the Greenland ice sheet would result in roughly a 6-meter or about 20 feet sea level rise, in which case this location, as well as my fine center next door, would be underwater, or at least be operated like we were in the Netherlands. And most recent satellite measurements from this and other satellites indicate that the ice sheet movement along the coast has actually accelerated. It is estimated that the net ice mass loss of 120 to 200 cubic kilometers a year is underway, which translates to a considerable sea level rise. Now, let's hit this right. In the next decade, we've got a number more satellites that are in development. I won't go into details about these, but these are very exciting. These were recommended by the U.S. Climate community, and they're designed to really nail the details of climate change so we can begin to actually devise various counters. Again, I won't go into a lot of detail, but there's the Ocean Surface Topography mission, which actually gives you really accurate measurements of the surface. That's what we're going to use to measure real sea level change. GOES-O is a new weather satellite, and it provides images seen on your local weather forecast. And the orbiting Carbon Observatory is the first ever, as I mentioned, measurement of the atmospheric carbon dioxide. Now, this is an example of the kind of data we take. This is real data. It was taken from 2 satellites and 2 instruments in thousands of orbits. And this is a time lapse over a complete season where 1 second represents 1 day. So this is a 5-minute long movie. So as it goes through, I'll talk a little bit about what it's showing. White is the clouds, and you'll note the daily pulsing as clouds form with solar energy and then dissipate at night. The color is the sea surface temperature, which slowly varies throughout the season. And the interesting thing here is that you can see the hurricanes. You can see some of the tracks on here of the named hurricanes, and if you watch carefully, as you see that as they go along, there's a blue path behind each of them. This is really showing how they pull energy from the ocean and leave behind a cool water. And now this season is the one that was of great concern because it's where Hurricane Katrina, which I think is coming up here pretty soon, arose. But this is the kind of data that NASA increasingly is getting, and it also begins to help us measure, are we seeing an increase in hurricane activity? And when you see some of this data, you begin to be quite, there's Katrina. You begin to see quite a lot of the concern that if we get a lot more hurricanes, the impact of a lot of climate change. When you look at this, it kind of looks pretty scary, and you don't really want to live in the southeastern part of the U.S. I use this with the agency to say that we don't really want to have those 3 centers in the southeastern part of the country. If you want to build things up, put it at Ames. Although they remind me there's some phenomenon called earthquakes that might not be such a great idea. Now, this is an example of observational data that is taken. The next one is a combination of observational data and theoretical calculations. And this is a high-resolution, 3-dimensional atmospheric simulation using the Columbia supercomputer. This is a computer that we brought up in 2004. At the time, it was the world's 2nd fastest computer. It is now probably 200th or 300th, although just today we dedicated its successor computer, the Pleiades computer, which in the benchmarking done a few weeks ago is the world's third fastest computer. I like to call it the world's largest non-naughty computer because the only ones that beat it were DOE bomb banking machines. But again, these are the kind of analyses that we can do to measure the precipitable water in the clouds, and we match that with the models to be able to move those things forward. Now, the next thing, of course, we can do fully theoretical analyses, and this is a simulation that shows us things that are impossible to observe by satellite. In this case, it is deep ocean currents. And this is a high-fidelity supercomputer simulation that shows the currents 15 meters below the surface. And this has a lot of significant implications for thermal balance in the oceans. The oceans have orders of magnitude more thermal energy than the atmosphere does. So understanding what's going on in the temperature, especially in the top regions of the ocean, really is one of the key drivers to global climate. And again, this is a longer set of simulations, and it's 1 second equals 1 month. Now, the interesting thing, these little flickers you can see, those are storms that have been artificially input into here, and you can kind of see how their impacts they have on heating and cooling the surface of the ocean. They quickly pump energy into the ocean, and then it's quickly dissipated. The shear products in the ocean are producing these little vortices, or sometimes called gyres. These can persist for years as you see them off the continents. And these are things that have major impact on continental climates and climate trends. Areas like Australia that have very, very radically changing climates, it's these sort of gyres can have a huge, huge impact. Now, one of the other features on this is these huge permanent polar vortices. And this is a connection between what we observe on the Earth and what we now see deep in space. When we look at Jupiter and Saturn, we also see polar vortices. So we're beginning to be able to take data not only from the planets and apply it to Earth, but the other way around as well. Now, none of this really means a lot if you can't move the data around. This is the internet in 1973. And just to kind of go back to history, when I was only about 60 years old. But in 1973, Ames became the 14th node and the first NASA center in the internet. We had the Iliac 4, which was our first supercomputer, and it was the first supercomputer on the internet. And the interesting thing is that we begin to develop the West Coast backbone that eventually developed into the internet, and it's kind of like a developing organism. The next step was we had the first trans-Pacific internet connection between what's Ames and Hawaii, and so this grew, and so NASA is really proud of our role in the past of where we're going. Now, as I mentioned, this is our newest entry into the high-end computing. This is a 487 teraflop machine that just started operating here this last week. And as I said, it was the #3 spot in the world, and it's in the top 500 list of the world's fastest computers. Now we expect to early next year to up this to a petaflop machine. So again, and it is the largest machine in the world that's really devoted to things such as climate science and other civilian modeling applications. Now, as we all know, the West Coast backbone evolved with the dominance of Silicon Valley and high tech, major universities and laboratories, and eventually industries such as you folks developed and the hardware along with it. So this is kind of a natural place for NASA to place its IT focus, which is what we've done. The next major effort, of course, is that we're deeply involved with how does one display this data. We have just established a new hyperwall, which was the world's largest display in terms of number of pixels until our colleagues at Calit 2 in Southern California added one more row of monitors to beat us. But don't worry, we're developing a long-range missile. Oh, that was a previous job I used to have. But at any rate, a lot of the work over at Ames is how do we take particularly climate data and display it? And what you saw was some of the efforts that NASA did to display data. Now, the next step is what does one do with all this data, and how does one handle it? There was another thing developed in the 1960s, which was the operations center that was based on digital displays of data, digital data. These are now used everywhere from police dispatch to Wall Street to operations in any particular area. But again, I think NASA can take credit for inventing this this architecture, which is known as mission control, developed for Apollo. This, by the way, was the Apollo 17 photograph. You can see one of our very famous operators, Gene Kranz, there in the lower right. And this is now being used everywhere. And this was an example of mission control architecture being used locally. This is the San Diego Emergency Operations Center, stood up in October 2007 to fight wildfires in Southern California. On the left is a display of NASA collaborative decision environment showing fused UAV data with satellite data in real time. And I might add that we used Google platforms for this, so thank you. But this is the kind of data that we received from the satellites. This shows the visible smoke and infrared in the fires from the MODIS imaging spectrometer on the Aqua satellite that I mentioned earlier in the A-train. We did the same thing again this year with expanded data. We also used the NASA unmanned aerial vehicle, ICANA, which I'll show you in a second, to get more detailed data. The interesting thing is this was the only way to really see through the smoke over the fires, to really plot the development of the fires and help the firefighters do their work. This is the ICANA aircraft, which is the DoD called this the Predator, but that's not a very nice name, so we use the Native American Choctaw word, which means intelligence. And we painted it white rather than black because we're the good guys. But this had a Ames-developed multispectral imaging pod on it, and it was the first use of an unmanned aerial vehicle in national airspace, so it's kind of a neat effort. But what we were doing was actually taking these images, rectifying them, putting them on the platforms that you folks had developed, and putting other data on it, and it was sent via satellite to a website hosted at Ames, and we created files for Google Earth, and then put those on servers. And that allowed the firefighters then to use this to vector in their efforts and to understand where the actual fire front was. This last year, we were credited with saving the lives of several dozen firefighters with this data, because it enabled them to know they were about to be surrounded so they could actually leave the area. So this is another example where NASA's Earth science data, coupled with our methodology that we developed for space exploration, could be applied to solving terrestrial problems. Now, let me bring something much closer to home. Those of you that know me know that I'm a wine enthusiast. Some would say lush. But over the last few years, we've begun a collaboration with the California vintners to begin to manage the impacts of seasonal weather and provide irrigation forecast. And this is really where we're going in the future. One of the key questions that somebody has, if I tell you the climate's going to change by 8 degrees over the next 50 or 60 years, you say, okay, that's nice. What I really want to know is, what's this mean for me? Does it mean that Google needs to build all the buildings on stilts? Does it mean that the vintners need to plant Cabernet rather than Chardonnay? Probably. Cabernet's better anyhow. But so this is an example of a product that we've worked with the Robert Mondavi Vineyard that enables us to use NASA data to measure the water soil content, so they can use this to better meter out the irrigation water they use. The next thing, of course, is looking at growing season anomalies and making predictions into the future. So we're beginning to take theoretical data, to use a synthesis of models as well as satellite data to give these folks information. Now, the interesting thing on this is that the climate varies incredibly, as any farmer could tell you, but for the first time they might actually be able to have some data that is better than the Farmer's Almanac as to how to water, what to plant, and how to plan for the next decade. So this is a product I think you're going to see a lot of work on. I was at a meeting a few weeks ago sponsored by Lieutenant Governor Garamendi. The state of California, even in its budget crisis, is intending to set up a detailed climate prediction center. We expect within a few years that in addition to the weather forecast you'll get a climate forecast, so you can begin to understand what does it mean for long-range planning. Let me turn to another topic. This is Chicago at night. You can see money changing hands right before your eyes. This is from a current satellite called the Defense Meteorological Satellite Program, and it's a 30-year-old technology. However, this is an example of what you could get. You could actually see who is changing money, maybe. This is an image from a handheld camera on the International Space Station taken by Don Pettit on Expedition 6. And this begins to give us the kind of data where you can do urban planning. You can understand the energy usage. You can help urban planners figure out where light's being used and not used correctly. We've signed some agreements with the city of San Francisco, as well as the beginning to work with the city of San Jose to begin to use NASA data to do detailed urban planning, so that we would eventually be able to take data like this from something called a NightSat that would enable them to tell in real time what's being used and what's not. In fact, it's interesting, in the area on the right is an area where the corruption hasn't completely been rooted out either yet. But you can see a major impact there in the Washington, D.C. versus the suburban areas. You can see the square of Washington, D.C., the light usage policies have considerably different light usage than in the suburbs right outside them. So this enables city planners to begin to look at this. On the left, you can see the San Francisco Bay Area, and you can see the effect of the urban planning in keeping the forest areas in the Berkeley Mountains as well as Santa Cruz Mountains free of urban regions. So this kind of study and analysis really, I think, is going to be a major input into future city planning, and I think we're going to have a lot of efforts. Now, NASA's doing a lot. We're interested in deserts, and this is a painting of one of our satellites, because we couldn't get a picture like that as it would appear in space above a desert. But the interesting about this desert, it's on Mars. And this is one of the many images that we've gotten from a lot of our satellites over Mars. This is telling us a lot of the typical desert features that we see on the Earth: mountains, erosion, and weathering. But Mars is an interesting planet. It's one of the most Earth-like planets in our solar system. It's a 24-hour day. It's got an atmosphere, polar caps, seasons, even has snow, as we found from our Phoenix lander, and almost certainly had oceans. But it's a desert planet now. And understanding the processes that occurred on Mars will better help us understand a lot of the desertification processes on Earth. So as we embark into the solar system, a lot of these programs have direct feedback to Earth. Now, this is a different planet. This is Venus. It's a relatively Earth-like planet in some senses, but it's almost the opposite of Mars. It had a runaway greenhouse effect. But it's very similar, as far as we can tell, to the early Earth before life evolved. So one of our key points here is by studying these planets, we can begin to understand these processes better, that we're trying to steer a course between a Mars future and a Venusian future, neither of which is very desirable. Now, this is another area that NASA is looking at, which is, I think, very exciting. This is cyanobacteria. Now, I'm an astronomer by background, and so the biologist told me that, I said, well, what is cyanobacteria really? It sounds a little complicated. And they said, well, you know it as pond scum. And this arguably was the first life on Earth. It's the first life that we have fossils from. It emerged over 3 billion years ago. And there are some that believe that it might have emerged on Mars first and migrated to Earth through asteroid impacts. But why this is such an interesting organism, and why I put it up here, is cyanobacteria transformed the Earth's atmosphere from a carbon dioxide methane mix, toxic to all higher forms of life, and probably similar to what the current Venusian atmosphere is, to our present nitrogen-oxygen atmosphere. And so this is really what made this planet capable of supporting life in all its diversity. And we've built a lot of these planetary monitoring systems to figure out how we can survive outside the Earth. We're doing a lot of things like developing solar panel technology, photovoltaics, and other things that look like they have a considerable impact on terrestrial life. One of the other things we are doing is looking at some of these life processes. This is a membrane technology for water treatment. This was work, by the way, funded by Google, which we thank you for. And these are forward osmosis membrane elements, each approximately a meter squared. And we can filter out water, but also with a lot of ions in it, you can actually pull energy out of it. I'm reminded that there appeared on YouTube here a day or two ago a rather humorous discussion of drinking urine that was sort of taken off of one of our researchers, showing that you could process urine through one of these kind of things and actually drink it. So if you haven't seen it, I would commend it to you. It's quite amusing. I'm going to have some of our staff practice that. But one of the other things we're trying to do is to look at how we can extract biological molecules. This is a self-assembling synthetic multi-enzyme complex for bioremediation that we actually extracted from extremophile proteins. This is work that, and by the way, it says do not post, but I posted it anyhow, so Jonathan Trent will be quite happy because he wants people to call him. But this can transform cellulose biomass into usable fuels, like green aviation fuel from green algae. We are also looking at using cyanobacteria, which is blue-green algae, and green algae is a way to produce biofuels. So all of the work that I think you're going to see out of, or much of the work out of NASA in the next decade is going to be focused very much on some of these biological processes. So, really in conclusion, why are we doing all this? And I think it's really, in summary, it's fun, it's profound, but I think it's really important that this all comes back home, is that NASA's work is designed to make life better on Earth. And I really would invite all the folks at Google and elsewhere to join us, collaborate with us, and we invite you to come and work with us. We've been at this for 50 years. This is our 50th anniversary this year. Well, all I've really got to say is you ain't seen nothing yet. Well, let me stop there and be happy to answer any questions. But again, the Earth part of what we do is going to be a big thing in the future, and we look forward to working with everybody. Thank you.
If there are any questions for Dr. Warden, please come up to the microphone.
So when you've got large-scale imagery like this showing the planetary atmosphere, it's almost like you can have 1,000 laboratories at once. You can see the impact of certain volcanic emissions on the atmosphere and their thermal properties. You can see the impact of urban areas, et cetera. I was wondering, are you starting to look at those to help validate models for global warming to see, for example, it's like doing an experiment, you're injecting more methane here or you're injecting more CO2 there, to actually see if the models really make sense, testing it experimentally as opposed to a regressive type of model?
Absolutely, and that's really where most of the research is now, is to begin to actually take real data and connect it with the models. And we've sort of begun to do that in some of the data I showed you, looking at natural inputs to the such as storms and so forth. The next step, and the one we're beginning to, is to make experiments, like you say, with volcanic eruptions to try to see if we can see those impacts, pollution from cities and so forth. And so you're kind of a good straight man, because that's where the next bit of work is. And we're just now beginning to get enough accuracy out of the space data and also airborne data. I want to emphasize airborne data is really critical, because the satellite only comes over a couple times a day. When you find something interesting, you put an airplane over it for a long period of time. We're very interested in that, and indeed, a couple of things that we're doing is looking at UAVs, and you might notice there's an airship flying over at Moffett Field, and we've made a deal with the Airship Ventures guys. We're going to put some sensors to start doing some of that. But the hard part is getting that model with enough fidelity so that you can begin to actually see what those micro inputs are and how they impact, and begin to make micro predictions to say that what the climate is. And I would judge in the next year or two that we're going to begin to get some real results on that, where we can say the city of San Francisco did this policy, and that had this impact on the regional climate. Some other city changed light efforts and energy usage patterns, and begin to see some climate changes. But that's where it really begins to get exciting, because now it's a tool for management. That you might say, all right, somebody decided to change water usage. What did that do? Did that help or hurt in certain areas? So that's kind of where we're going, and I'm really looking forward to some of the first results.
Welcome to Google, and thank you for sharing this presentation with us. I've heard a lot about you from your NASA colleagues. They've been very, very positive and excited about you. And I wanted my question to be a little bit more strategic in nature, because you're a person in a very strategic position right now. I mean, I can get all the details about this great Earth science, like from the web and from NASA's great websites. But what I'm really interested in, and I'm following on the presentation given on the 50th anniversary of NASA by physicist Stephen Hawking, who said that we are not investing enough. I mean, the amount of money, and we're talking about money these days, even colleagues of yours like Alan Stern in the New York Times, who views like some of this as a waste of money, whereas we know, we who follow space science, that it's actually less than 1% of the U.S. budget that is spent on space exploration. And following on what Stephen Hawking said, that we should be really increasing, because this money invested in space exploration is investing in our future and in inspiring future generations. So, and plus saving the Earth from ourselves. So with that in mind, I have a very simple question. When are we going to see humans on Mars?
Interesting question. I certainly love to see us spend more money. I hope we spend more money. But as I used to say when I was in the military, that's above my pay grade. But let me kind of answer your question. It's a fairly, and if you'll pardon me for being a little long-winded here, there's kind of three things that NASA does. And the first one is science. And let me put Earth science in a separate category. Not that it's not science, it's very important science. But in the basic sciences, NASA has, and its colleagues around the world, but mostly NASA, has revolutionized physics in the last decade. We now know that what we are and what the matter we see is almost nothing. It's less than 1% of what the universe is. And this is the most exciting time in physics for a century, since quantum mechanics and general relativity, maybe even more exciting. And because it's interesting, because every new discovery tells us we know less about the universe, and that's exciting for a scientist. It says there's an unlimited set of things to do. The next decade is going to be, I think, the decade of fundamental biology discoveries by NASA. And of course, you might know the astrobiology institutes at NASA Ames, that we are going to, I think, answer the question, where else is there life in the universe? Is it in the solar system? Is it in other planets around nearby stars? Missions that are being worked, like right here. We're going to launch here in a couple of months something called Kepler. It'll be the first mission to discover or see if there are Earth-like planets around other stars. So we're going to, and I think within a few years later, we'll see whether they're life-bearing. So this is a very interesting effort, but that's the first thing we do, and that's very exciting. This is the most exciting time to be in science and at NASA, because we're changing the whole field. We're upsetting lots of apple carts. And as a scientist, I love that. The next thing, of course, we're doing is what the question that you raised is exploration. And let me come back to that in a second. The third thing we're doing is to help people on Earth. And I talked about Earth science, specifically kind of site-specific predictions. We do, the first A in NASA is aviation, and it's the aeronautics administration. I think that one of the major things we're going to do in the next decade is revolutionize air travel. We're going to have to build carbon-free systems eventually, and at least starting with carbon neutral. That's going to be a major job for NASA. But the third thing that we do is really beginning the settlement of the solar system. And all these are pretty exciting. And I didn't talk about the settlement of the solar system, but probably about well over half of what NASA does is to do that. We're in the process of building the basic systems today. Of course, there's a lot of controversy. Is this the right rocket or isn't it? I'm not going to get into that. Those are discussions over many beers, other than to say that I was on the study teams that validated those, and I initially was a skeptic. And Mike Griffin put me on the study team, and he said, your job is to be, well, he used the word to begin with A. And after a few weeks, he said, you're doing your job extremely well. But again, I think we're making that progress. But the question is, okay, where are we going? And when you say settle the solar system, what is the target? And I'm convinced that Mars is clearly the location that could support large-scale human settlement. So Mars has to be regarded today is the target for settling. Now, there's a lot of steps to get there. I think the moon is an initial step. The next one, and maybe even simultaneously with the moon, are near-Earth asteroids, where you can, because they're stepping stones to Mars. In fact, I think eventually a human mission by 2030 to Phobos could be done using the hardware that we're building today. So that becomes a significant step. Now, what NASA and our partners around the world need to do with Mars is find the resources, figure out, is there life there? In fact, if we find extant life, that's going to change a lot of things. Are we compatible with it or not? If we interfere with it, is that appropriate or not? These are going to be fundamental philosophical issues. But let's assume that, whatever we find is reasonable for us to settle there. I believe that sometime after 2030, after NASA and its colleagues mount human missions, probably not to the surface, but to someplace like Phobos, and coupled with a robotic colony of some form on the surface, that we will enable private sector settlement of Mars. A one-way mission to Mars is a quite feasible thing to do if the government didn't do it. And in fact, I've had discussions with some senior officials here at Google that are very interested in that, and I fully support them, and I suggest that they invest their money in that. But I think that we will see private sector missions. I think that they could be done in the order of $1 billion or $2 billion, which is kind of money that can be raised privately for these kind of things. And I think that what the government's job to do is to pathfind what's there, what are the resources. In fact, I think probably they'll end up sealing a cave and living in that for a while. What's the technology, the communication systems, the power systems, and do that basic technology development and demonstration. So I'm pretty optimistic that sometime post 2030 we will see real human settlement on Mars, but funded not by governments, but funded by private individuals. And that's sort of what the vision that I would see for the future.
Pete, can you tell our audience, what does the preeminent space agency in the world think of things like the Google Lunar Xprize? And what specifically do you think NASA might get out of the competition?
It's kind of you're a good straight person. I think the Google Lunar Xprize is shit hot, to use the current word. It is exactly what we ought to be doing, and I am delighted that the Google leadership stepped up to that, because I think that's going to make that first step, is to have private sector folks go to the moon and demonstrate a robot on the moon. In fact, we have just submitted a proposal at NASA Ames in conjunction with one of the teams that we said that they promised when they went there they would carry along a 5-kilogram payload that NASA has to measure the toxicity of the lunar dust. We'll see how our proposal fares, but this partnership, again, between the public and private sector, where Google has kicked off this interest, and I'm convinced there's at least 3 or 4 of these proposals that are very credible. This one was particularly credible because it used some designs that we had done, but there are, and I won't advertise which one, but you can probably find on the web which one. But we're also in discussions with some of the other teams, but where NASA could be a customer is what we want to do, and that's one of the steps that we're starting to do. Our preferred approach is to have the space station serviced and passengers taken to and from it commercially, and I'm convinced that's going to happen probably a lot sooner than people think. The next step is to have commercial entities fly me to the moon and fly initially robots and capabilities. That, I think, will begin this effort that will lead to private settlement of other planets. And at that point, the government has done its job. We've done in space what we did in aeronautics in the middle of the 20th century. Very few people know our predecessor agency, NACA, the National Advisory Committee in Aeronautics, was indeed the key thing that allowed America to build its preeminent aviation industry by assisting it. And we didn't do the work, but we helped them. We had laboratories, we could do key testing, develop technologies, and work with the companies. So this is very exciting, and I really thank Google being one of the first partners that's willing to kind of step forward and say, okay, if they can get to the moon, we'll give them a prize. So my thanks to our host today for doing that, and I think it's going to pay huge dividends for everybody.
All right, well, let's give Pete a round of applause. Thanks for being here.